Hello and welcome to another episode of Study Session for AP Physics 1. In this video, we will be covering linear momentum. Okay, so basically, to start with momentum, we need a couple basic principles that we need to kind of get out of the way. So first, momentum is always conserved unless an outside force is acting on the system. So the momentum within a system will always remain the same. You know, the total momentum, the sum of all the momentum in the x components and the sum of all the momentum in the y components. And if you take AP Physics C, you will learn it also holds true for all the momentum in the z direction. So your initial, we'll just call this, so the designation for momentum is a p-looking character. And I believe it's the Greek letter rho. I'm not 100% sure on that one, but regardless, it's basically a p. And so if we say px not equals px final, it's really, I think it is rho, but I'm not 100% sure on that. So I'm just gonna call it a p because it looks like a p. Let's be realistic. You don't need to know the names of the Greek letters for AP Physics 1. So py not equals, this should be an f, sorry. Py final, and then py, or pz, sorry, not py, pz equals pz final. Okay, and the second concept to understand is that an elastic collision, so I'll just call that E collision, kinetic energy equals conserved. So basically, the kinetic energy initial will equal kinetic energy final. And an example of an elastic collision, typically it will state that if it's an elastic collision or not. But you know, if you have two like hard balls colliding, normally those are elastic. And then like if you have a wall and a ball bounces off, or ball comes at it with velocity v, and then it bounces back with velocity negative v, that would be elastic. So if you think about it, formula for kinetic energy is 1/2 mv squared. Mass isn't changing, the wall doesn't move after it, and the v stays the same. So therefore, the kinetic energy will be the same before and after. And then the second type of collision is inelastic collision, so E, N, and then that would be where kinetic energy is not conserved. Equal is not conserved. And basically that's any time that kinetic energy before does not equal kinetic energy after. And typically the way it will be phrased whenever it wants an inelastic collision is like there's some sort of damage or whatnot, or like let's say they compress, a car runs into the bumper of another car and there's damage or whatever, or like a ball hits another ball, but then after the collision they stick together and move with velocity v or whatnot. Those are all inelastic collision examples. Okay, and then the third concept to cover is impulse. So impulse equals force times time equals change in momentum. And then that's just basically a form. It's just a way to solve for the force that's acting on the object per given amount of time to produce the change in momentum. Okay, so let's get into some practice problems. Let's quickly erase all of this. Okay, so the first problem says an object with a mass of 2 kilograms, so 2 kilograms. Oh, and sorry, momentum equals mass times velocity. I forgot to mention that, but momentum equals mass times velocity. That would probably have been helpful to know, but there you go. Okay, so mass of 2 kilograms has a linear momentum of magnitude of 6 kilograms times meters per second. 6 kg meters per second. Okay, what is the object's kinetic energy? Okay, so first, I know that kinetic energy equals 1/2 mv squared. So I know the mass already, so the only variable I need is velocity. And I can figure out velocity using the momentum equation. So 6 equals 2 times v. So then v equals 3, and ke equals, ke, I don't know why I put a plus, equals 1/2 times your mass, and your mass is 2 kilograms, times your velocity squared, so that's 3 squared. 1/2 times 2 is 1, so I'm just going to call that 1. 3 squared is 9, so equals 9 joules. Okay, on to, I don't want the soft eraser, I want the hard eraser. I wonder if there's a way I can move those around, so then I don't have to pull it down. You know what, let me try that. I don't know. I'll have to look at that later. I bet I can, though. Oh well, I'll figure that out later. A ball of mass of 0.5 kilograms, so 0.5 kg, initially at rest, acquires a speed of 4 meters per second, so 4 meters per second, immediately after being kicked by a force of a strength 20 newtons. 20 newtons. For how long did the force act on the ball? So here's where we have to use change in momentum, the impulse equation. So we know that force times time, so force times time equals your momentum final, so m times vf minus m times v naught, so your initial velocity, equals, your impulse, right? So if we plug this into the formula, we got 20 newtons times time equals our mass. So I'm just going to factor out the mass here because I can factor out the m. So 1/2, because 1/2 is equal to 0.5. 1/2 times your velocity final, which is 4, minus your velocity initial, which is 0 because it was initially at rest. So if I multiply that out, I get 2 equals 20t. So thus t equals 2 over 20 equals 1 over 10 equals 0.1 seconds. Okay, on to the next problem. Okay, a box with a mass of 2 kilograms accelerates in a straight line from 4 meters per second to 8 meters per second, so 4 meters per second to 8 meters per second. Okay, due to the application of a force whose duration is 0.5 seconds. Find the average strength of this force, so 0.5 seconds. Okay, so we're going to use that same impulse change in momentum equation as we did in the last problem. Okay, so we've got 0.5, which is our time, times our force, equals 2 times 8 minus 4 equals, so that all equals your impulse, right? So I'm just going to call 0.5 1/2 again, just because it's easier to deal with fractions than decimals whenever you're doing mental math. Equals, so 8 minus 4 is 4, so 2 times 4 is 8. So we then know that our force must equal 16 newtons because 8 times 2 is 16. Okay, next problem. Okay, a ball of mass m, okay, so this one is just variables, is traveling horizontally with velocity v. Okay, so velocity horizontal strikes a massive vertical wall and rebounds back along its original direction with no change in speed. Okay, so let's draw this out real quick. So the ball's moving like this. It comes in with v, and then it leaves with negative v. Right? What is the magnitude of the impulse delivered by the wall to the ball? Okay, so your impulse equals your change in momentum. So I equals delta p equals m times v final minus v initial equals m times negative v minus positive v. So equals m times negative 2v. And it simply wanted magnitude, so magnitude does not account for direction, so that just equals 2mv. There we go. On to the next problem. Okay, two objects, one of mass 3 kilograms, so 3 kg, is moving with a speed of 2 meters per second, so 3 kilograms to, actually I'm not going to put, I'll just put plus 2 meters. I'm just going to remove that altogether. So 2 meters per second. Okay, and the other of a mass 5 kilograms and 2 meters per second. So 5 kg, 2 meters per second. Okay, they move toward each other and collide head on. If the collision is perfectly inelastic, so perfectly inelastic, that tells us that these are going to stick together and have the same velocity after the impact. So that's basically what that's saying. Find the speed of the objects after the collision. Okay, so we can use the principle of conservation of momentum here. So I'm going to go ahead and call this velocity negative because we know that both the objects are going towards each other. So one must be moving in a positive, one must be moving in a negative direction. Okay, so let's use the conservation of momentum property. So 3 times 2 plus 5 times negative 2, because that's the sum of all of our, or that's our momentum to begin with. Like, that's a net momentum to begin with, equals the sum of all of our masses. So 5 plus 3 times our velocity final, because the velocity final is going to be the same, and you could factor that out. That's why you can do 5 or like 8 times VF. So let's solve for this. We got 6 plus negative 10 equals 8 times V. Okay, so 6 plus negative 10 is negative 4 equals 8 times V. So we then know that V equals negative 1/2 meters per second. And the negative simply tells us that it's moving in the direction that the 5 meters or 5 kilogram object was moving in before. And the answer in this case is positive 5 meters per second. But it doesn't really matter if it was positive or negative, because they could have defined the 3 kilograms mass as moving in the negative direction and then 5 in positive. It's all just, whatever you define as moving in what direction, because it didn't specify. If it had specified, then it would have been different, but it didn't specify. So yeah, I mean, and probably even asked for magnitude too. I just probably didn't read it. I don't know. But okay, next problem. Object 1 moves towards object 2, whose mass is twice the mass of object 1. So O1 equals M. I'm just going to call that MO1. MO2 equals 2M. Okay? And object 1 is initially at rest, so 0 meters per second. I'm going to make that an arrow. A bad arrow, but it's an arrow nonetheless. There we go. I'm just making it worse, whatever. After the impact, the objects lock together and move with what fraction of object 1's initial kinetic energy? Oh, sorry. So object 2 is at rest. I just misread it. Okay. Let's go to pen. And 0 meters per second. So, okay. So we know that conservation momentum is going to hold true, right? And our initial kinetic energy, so this is moving with an initial speed v naught. So our initial kinetic energy equals 1/2 mv naught squared. Okay, so let's remember that. So we know that mv naught equals m or 2m plus m times our velocity final, because they're moving with the same velocity after, because they stick together. So that sums up to 3m. We can divide by m on both sides and cancel that out. So we get that v final equals 1 or v initial over 3. Okay, and now we simply substitute this into our kinetic energy formula, and we get that k final. So I'm going to call this k naught equals 1/2 times 3m times v naught over 3 squared. So that's going to square up to, so this is going to square, and then this is going to turn into 9. However, we're multiplying by 3, so then that's going to be 3. Okay, so we end up with 1/6. So our k naught equals 1/2 mv naught squared, and our k final equals 1/6 mv naught squared. Okay, and if we want to find what fraction of the original, we simply put this over that, and then we end up with 1/3 of that, because 1/6 divided by 1/2 is 1/3. So we get 1/3 of our original kinetic energy. Okay, so that will be all for this video. Hopefully this helped you guys out. If you need any more help, be sure to visit my website, studysession.org, so www.studysession.org, and be sure to ask any questions you have on the forums, and I will do my best to answer them. Pretty much stay tuned for more videos, and I will see you guys next time.